All right. Good morning, everybody, and welcome back to Math 115. So today we're going to continue our discussion about trigonometry. But first, for my 7 remaining live students, how are we doing? We surviving out there? Has it been a rough week? Very tired. I feel that. How about everybody else? We're up to 8 now. Catching up on sleep this week, yeah. Doing well, that's good. Extremely difficult. Oh yeah, allergies are coming. I've been a little bit stuffed up as well. Yeah, I feel like for me, I'm sort of finally. Car is covered in pollen. Yeah, I don't even see that much here for some reason. Yeah, I feel like I'm sort of finally awake at 8:30 a.m. and now it's Thursday, so it's like just in time for me to like totally screw up my entire sleep schedule over the weekend. And then we'll just like repeat the process. All right. Well, glad to hear everybody's doing well, and doesn't seem there's anything majorly wrong other than the obvious thing that's wrong with the world in Atlanta. But sadly, that's not the subject of this class. All right. So let's see where we were last time. Today, I'm going to try to sort of breeze through a lot of material, okay? And it's going to be, and the material's not trivial, okay? It's a little bit tricky to understand this stuff the first time you see it. So if you struggle with this lecture, I just want you to know it's okay. Tons of people struggle with this the first time they see it. I struggled with it the first time I saw it. So don't feel bad. You just need to have some persistence. And if you don't get this right away, it would be a good idea to go to the SI sessions or come to my office hours or send me an email or look up some Khan Academy videos on YouTube or whatever, something to somehow supplement what we're going to talk about today because it can be pretty tricky. Before we talk about the new stuff, let me remind us of where we kind of left off. So yesterday we talked a little bit more about trigonometric functions, and specifically after we had kind of wrapped up our discussion on identities, we moved on and talked about, okay, well, do these functions have even or odd properties? And it turns out that they do, and most of them are odd, but a couple of them are even, okay? And the 2 which were even were the ones which had to do with cosine, okay? So cosine is an even function, and secant, which was given by 1 divided by cosine, was also even. And all of the rest of them are odd. Okay, so we have that kind of property which came from basically, well, if we consider what does an angle look like, and if we take that angle and make it negative, what's the relationship between the 2 points which we get on the unit circle? Well, the relationship is that the y-coordinate is flipped and the x-coordinate stays the same, okay? And it doesn't matter what theta is. If theta was originally over here, again, we get the same thing. The negative theta is going to be down here. And we're going to get, again, we're going to have originally xy, and then we're going to have x comma negative y. Okay, so what's really getting flipped here is the y-coordinate when we use a negative angle. And since all of the trigonometric functions are defined through these 2 points, or through the point on the unit circle, right? They're defined as a ratio between y and x, or they're defined as y itself or x itself, and these sorts of things. So when we flip that y-coordinate, we're going to get kind of relationships where some of them have been negated. And that's when we have an odd function. And if we have something which deals purely with x, like cosine or secant, then it's going to be even, and we're going to get the same thing for both of those angles. So that was about even and oddness of the trigonometric functions. And then we started talking about graphs of trigonometric functions. And we didn't really actually get to graphing trigonometric functions, but we're going to get to a lot of graphing today. But the first things that we excuse me, had to establish before we kind of talk about the graphs of these functions are, well, what are the domain and range? So we always want to know what the domain and range are, and the domain is always representing the inputs. So what are all of the inputs that we can use with a trigonometric function? Well, for sine and cosine, we can use any input that we want. Okay, we can use any angle, and we're going to get a point on the unit circle, and that point has an x-coordinate and it has a y-coordinate. So we can use any angle we want with sine and cosine. So their domain is all real numbers, where the real number is like, you know, we would take sine of that real number in either degrees. So if the real number is r, it's either sine of r degrees or sine of r radians, something like that. It doesn't matter which measurement we're using. It's just a different rescaling of the entire real line. You know, if you want to think about the entire real line in terms of meters or in terms of inches, it's still the entire real line. That's the amazing thing about it, is it's infinitely long in both directions. So if you want to get to 10,000 meters, you just go further out than you go to get 10,000 inches. Okay, and then the range is just going to be basically, well, what kind of values can this function produce? And the function produces the value of one of the coordinates on the unit circle, and it's either the x-coordinate or the y-coordinate, depending on if it's cosine or sine. And we just want to consider, well, okay, what's the maximum like x-coordinate we could have? Well, it's 1, because I mean, we couldn't have a point with an x-coordinate which was more than 1, because then it would be in sort of this region, which is highlighted in yellow, and there's no way we're going to be on the unit circle if we're that far out. So that's how we understand the range of cosine, as we consider, okay, what are the possible values which we can get if we plug an angle into the function cosine? And that's going to be all of the possible x values of points which are on the unit circle. And those x values range from -1 to 1, depending on where we are on the unit circle. And likewise, the height of a point on the unit circle also varies from -1 to 1, depending on where we are on the unit circle. So that's about the domain and range of sine and cosine. And basically, every other trigonometric function, their domain and range is going to be decided by looking at, well, what is the domain and range of the functions which make them up? Okay, which, like tangent, for example, is sine over cosine. So we might want to consider, well, we don't want to include anything in the domain of tangent, which is going to cause the denominator of that fraction to be 0. So there's going to be a little bit more thought that goes into the domain and range of the other trigonometric functions, but it all sort of stems from the domain and range of these two. Okay, so that was the domain and range of cosine and sine. And I'm going to redo this conversation about what are the zeros of sine and cosine now, just because I felt like I had to rush, and I don't like rushing, so we're going to go back. But before we do that, let me ask the class if there are any questions regarding this material that we've talked about so far, because we kind of had a lot of stuff going on. So I want to see if anybody during the recap thought of something which they're now confused about. And I don't mind going back and spending a little bit of time talking about any of those topics. Come on. Okay, if there's no further questions about that stuff, then I'm going to go back and talk again about more properties of these functions. Okay, so just like when we had the graph of a rational function, we kind of put together a list of criterion of what the graph should look like before we tried to actually graph it. And that's sort of what we're doing right now. So the first thing was to understand, well, what is the domain, i.e., which x values am I going to be able to plot a point for? And then the range was like, okay, well, what are all the y values going to look like on the graph? And now we're going to talk about what are the zeros of sine and cosine, i.e., where is the graph going to pass through the x-axis or the theta axis, as we're going to see. So we wanted to know, okay, well, what angles theta can we plug into sine and produce a value of 0? Okay, so let's remember what sine is. If we have an angle, theta here, and a point x comma y, the value of sine is given by, well, we make the angle, we make the line which goes to the outside of the unit circle, and then we check what is the point x comma y by using maybe the triangle or something like that. And then we check, okay, well, what is that y value? And whatever it is, that's what we call sine of theta. So if sine of theta is going to be equal to 0, then we want the point which theta produces on the unit circle to have the form x comma 0, where x is an x value and we want the y value to be 0. And there's exactly 2 points on the unit circle which produce, there are exactly 2 angles. Well, that's not exactly true. Let me rephrase. There are exactly 2 points on the unit circle which have a y value of 0. And they are not there and not here either. Please don't. Please, no. No. I just want this orange thing to go away. Okay. That was sad. Let's get our vertical axis back. All right. And there are this point here, which is the point 1 comma 0. That has the form x comma 0. And we also have this point over here, which is negative 1 comma 0. So our goal here is really to find, okay, what are the angles of theta which point at either of these 2 points? Okay. The first angle that obviously points in the 1, 0 direction is the angle 0 degrees or 0 radians. So sine of theta will be equal to 0 if theta is equal to 0 radians. Or, well, what if we point directly to the left? Well, if our angle goes directly to the left, Let me use a new color. We'll use this lavender color. Ooh, that's kind of hard to see, actually. Man, half of the trouble is getting the right color. We'll use orange. If my angle points directly to the left, and here's my theta, well then theta is exactly halfway around the circle. And I know that all the way around the circle is 2 pi radians. So I know that theta equals pi radians, which is halfway around, will also produce a sine value of 0. Okay, and likewise, if I go all the way around the circle, use blue. If I go all the way around the circle and I have a new angle which is pointing directly to the right, okay, so if I go theta equals 2 pi radians, then we're back facing 1, 0 again. So theta equals 2 pi also produces a sine value which is 0. Okay? So we have the following. We have sine of 0 equals 0, and we have sine of pi is equal to 0. We also know that sine is 2 pi periodic, which means that for any angle, if I go an additional 360 degrees around, or if I go an additional 2 pi radians around, and wind up at the same angle facing the same direction, then those angles are coterminal, and sine produces the same value for coterminal angles. So I also know from these two facts, plus the fact that sine of theta plus 2 pi times n is equal to sine of theta, then this gives me that sine of theta, sine of 0 plus 2 pi n for any integer n is also equal to 0. And we have that sine of pi plus 2 pi n is equal to 0 for any n, where n is an integer. N is an integer. Sometimes we say n is, we use this symbol for in, and we use this crazy symbol to represent the integers. So this statement here means n is an integer, basically. N is a number which is included in the set of all integers. Okay, sometimes we write that. All right. So what does this really mean? If we combine these two facts, then this just means that, well, for any even number of pi's, we're going to get 0, and for any odd number of pi's, we get 0. So really, this is just saying that for any multiple of pi, sine is going to be 0. So sine of n times pi is equal to 0. And that makes sense, okay? Why does that make sense? Because maybe I can do this. Oh, hell yeah. Okay, that'll work. Okay, so let me start here facing directly to the right, and let me call this angle 0 pi. Then sine of this angle will be 0. And then if I go over here to pi, then I will be having sine of 0. And then if I go around the rest of the way, and now I'm facing 2 pi, then sine will be 0 again. And then if I go around even more and I'm facing 3 pi, then then my angle will be 0. I'm sorry, not my angle, my sine will be 0. And then if I go around the rest of the way and I'm facing 4 pi, 5 pi, 6 pi, 7 pi, 8 pi, and so on and so forth, every time I hit a multiple of pi, my angle is going to be facing directly to the left or directly to the right, and that's going to produce a sine value of 0. So this is the property that sine has, is that at every multiple of pi, sine will take the value 0. Okay, and if you want to know what it looks like in degrees, it's sine of 180 degrees times n will be equal to 0. Because, well, 180 degrees is facing left, 360 is facing right, 540 is facing left, 720 is facing right, and so on and so forth. So this is how we get the sine, the zeros of the sine function. And it also works for any n which is negative, okay? We can do sine of negative pi. Well, what would that look like? It would just look like, well, we start facing to the right, and then we go halfway around the circle in the opposite direction. But that's the thing. If we go halfway around the circle, it doesn't matter which direction we go in. We're still going to be facing either directly to the left or to the right. Okay. So let me ask you guys, have I completely beaten this issue to the death or to death? Does this make sense, or is this kind of confusing? What do we think? Some feedback would be really helpful for me. I feel like it's a little better. Okay. This is going to come become more clear, I think, once we actually get to the graph. We're nearly there. But before I move on to the graphs, I want to talk about one more thing, and that's the zeros of the cosine function. Crap, I'm in trouble here. Let me see if I can move all this stuff up. Let me just delete that. I'm going to make an extra page here. Okay, so now let's talk about the next one, which is, well, how about what values of theta cause cosine of theta to be equal to 0? Well, if we have our unit circle, what that's really saying is, okay, I know that the cosine of an angle theta is going to give me the x-coordinate. So if I want the x-coordinate of the point on the unit circle to be 0, then there's 2 points which cause this to be true. It happens here at the point 0, 1, and here at the point 0, -1. So if we want cosine theta to be equal to 0, well, our angle better be facing either directly up, which would be a 90-degree angle, or pi over 2, or directly down, which would be a 270-degree angle, or 3 pi over 2, or go further around and however many revolutions we want to go to get to there. Okay, so we know that cosine of pi over 2, okay, that's this angle, which looks like this, basically. It's facing directly up. And this forms a right angle here. And that produces a value of 0. So we could have theta equals pi over 2, or we could have cosine of like 3 pi over 2 equals 0. And these are the two angles which are between 0 and 360, okay, which cause cosine to be equal to 0. So if we know that if any other angle, okay, if any other angle causes cosine to be equal to 0, then it had better be coterminal to one of these two, since these are the only two which are between 0 and 2 pi, which cause it to be 0. We can go around the circle 10 times and then wind up at facing pi over 2, but that's an angle which is coterminal to pi over 2. So really, once we know what all the reference angles are which cause cosine to be equal to 0, then all the other ones are just going to be cosine of pi over 2 plus 2 pi n is going to be equal to 0, right? Because that would be coterminal. And cosine of 3 pi over 2 plus 2 pi n will be equal to 0. So if we want to write this down, what it's looking like is, okay, we have pi over 2 is a yes, 2 pi over 2 is a no, 3 pi over 2 is a yes, 4 pi over 2 is a no, 5 pi over 2 is a yes, and so on and so forth. So it looks like we have like every other every other one here, right? And the way we can express this is, well, the denominator should be 2, and the numerator should be like an odd number, okay? The first one it's 1, the second one it's 3, the third one it's 5, and so on and so forth. So if we wanted to come up with a really good way of saying this, we could say something like cosine of 2n plus 1 over 2 pi is equal to 0. Because then this number on the top will be an odd number, because 2 times any number n will be an even number, and we add 1 to an even number, we get an odd number. And then we divide it by 2, and we'll get something like, well, if n is equal to 1, no, if n is equal to 0, then we get just pi over 2. If n is equal to 1, then we get 3 pi over 2. If n is equal to 3, we get 2, then we get 5 pi over 2, and so on and so forth. So this is how we can encapsulate this behavior here. It's really just to say, well, you can express an odd number, all odd numbers, as the numbers 2n plus 1, where n is an integer. Okay, so we take all the odd numbers and divide by 2, and that will give us all of the points which are facing either directly up or directly down. Okay. So this is how we figure out what are the zeros of cosine. All right, so let's actually talk about how we're going to graph this function. Okay, so what we're going to do now is we're going to set y equals sine theta. So we're going to graph the graph of an equation here where the height of the function is going to be the height of the point on the unit circle, which corresponds to the input of theta. And so here theta is actually on our horizontal axis. Okay, so if you want to call this y equals sine of x and put x here, that's fine too. I just like theta because I like to think about, well, theta is an angle, so I just like to write theta when I use the trigonometric functions. And so what we're going to do is, as I march along the horizontal axis, I'm going to consider different angles. And at a given point, say this point here is like, I don't know, 5 pi over 2 maybe. What I'm going to do is I'm going to then take that angle and I'm going to draw it on the unit circle. Okay, and then I draw 5 pi over 2 on the unit circle and it's facing like directly up. And then I take a look at, well, what is the point on the unit circle? And I take its y value and I plot that. Well, the y value is 1, so I plot a point whose height is the height of the point on the unit circle, which corresponds to the angle which is given from the horizontal axis. So this is the rule for how we actually are going to do this. Okay, so essentially, let me go down and show you what I mean. Essentially, this is kind of what we're doing. Okay, so we're going to take the angle pi over 6 here. We're going to put it on the unit circle. Okay, pi over 6 looks like this. And then we check, well, what is the height of the point on the unit circle, which corresponds to the angle pi over 6? And then we take this height. Okay, we take this height here. Oh, that highlighter doesn't show up very well. Why don't I draw it in red? Right? We take this height here in red, and we copy it over to be the height of the function at that point. Okay? And then we just move on to pi over 4, okay? Then we draw pi over 4. So pi over 4 looks a little bit different. It's a bigger angle. It looks like this, right? Here's pi over 4. And then what do? I just check what is the height of the function given by or what is the height of the point on the unit circle, which is given by this angle pi over 4, and I allow that to be the height of the function at that point. And so on and so forth. And so you can imagine that essentially as my angle here starts at 0, the height of my function should grow until the input reaches pi over 2, and then I should reach a maximum. So when the angle is pi over 2, that's when I reach this kind of maximal point up here at the top of sine. And then once I keep going with this angle from pi over 2, I go even further, then the height of the point as I go around the circle is actually decreasing. And once I get to pi, that is where the function is going to cross through the x-axis. And then as I go even further along, well, I go negative. And the points here have a negative height. So that's where the height is going to be negative on the graph of my function. And then once I reach this point facing directly down, well, that's when the negative is going to reach a maximum. So I know that when x or theta, if you want, is 3 pi over 2, then that is when the height of the function is going to reach a minimum, because it will be all the way down at -1. Since if I draw 3 pi over 2 on here, it looks like this. And I look at the point which it crosses through. This is the point 0, -1. And I take the y coordinate and I make that to be the height of the function. Okay, so this is how graphing a trigonometric function works. Okay, and this is why I really loved to include this moving image here. Okay, because this is basically what's happening with this middle graph here. Okay, the middle graph is saying, well, if we pause it for a second, you can see that the height of the squiggly is exactly the height of the point on the unit circle, which is given by the angle which points in that particular direction. Okay, and if we choose another point, here it looks like we're facing basically theta is equal to 0. We're facing directly to the right. And, well, what is the height of our function? It's 0. So we can actually tell this is even a sine graph, because the height of the function is 0 when the height of our point on the unit circle is 0, which means that the height of the function is being given by the y-coordinate of the point on the unit circle here, which is corresponding to that point. Okay, and this is how it goes, is as we go around, the height of the point which is on the unit circle is going to vary from -1 to +1. Okay, so we've actually, if we were to graph this, the horizontal axis would be like right here through the middle of this thing. And then once it goes through the point 0, well, each time that the graph passes through the point 0, then the hand on our clock here is going to be facing either directly to the right or directly to the left. Okay, so this is how we understand the graph of a trigonometric function. So let's actually do it for sine, and we'll see how we actually would do this in practice. So if you were asked to actually graph this function, we'll just go through one by one and do it. Okay? The first sort of good thing to do is to mark on here sort of all of the values of theta for which we can easily compute the value of sine. Okay, and I chose pi over 2, pi, 3 pi over 2, and 2 pi because those are the points which face basically directly to the right, directly up, directly to the left, and directly down. Okay? So here's how I'm going to graph this. Well, first of all, I'm just going to take the point pi over 2. So what does pi over 2 look like? It looks like an angle which goes directly up like this, and then I have an angle here which goes from the positive x-axis, it goes from the positive x-axis to straight up and down, and it's a right angle, and this is pi over 2 degrees, or radians. And then the point which corresponds is the point 0, 1. And I know that I'm using the sine function here. I'm trying to graph y equals sine of theta. So what I'm going to graph on here is going to be the height of the point, which corresponds to that angle, which in our case is 1. So at pi over 2, I make a mark at y equals 1. Okay, then if I were to draw the angle pi, well, what does pi look like? It looks like it goes all the halfway around the circle. Right? We start facing to the right, and then we end facing to the left. And this is the angle pi. And if I consider, okay, what's the point on the unit circle which corresponds? It's the point -1, 0. So if my goal here is to graph sine of theta, well, sine of theta is going to correspond to the y coordinate of that point. So I know that sine of theta is actually 0 when theta is pi. And so on and so forth. I can do the next one. Well, the next angle is 3 pi over 2. It'll be facing directly down, and we'll get this point here, which is the point 0, -1. And so I know that I should graph the point -1 when theta is equal to 3 pi over 2. And then again, when theta is 2 pi, we're facing directly to the right. So I should have a point here, which is going through the x-axis. And then likewise at 0, right, we have a point which is going through 0, 0, because if I do sine of 0, I get 0. And if I do sine of 2 pi, I get 0. And so you can kind of see, well, what's happening in between? What's happening in between is we're kind of having a smooth transition up from 0 to 1. Okay, we're having a smooth transition up from 0 to 1. And basically, as we get closer, okay, one thing that we should notice is that as we're very close to the angle 0 here, the height of the function is rising somewhat rapidly. For a relatively small change in the angle, we get a pretty big change in the height. Okay, but if we compare that to what's happening close to the top, a relatively small change in angle is actually kind of corresponding to a pretty small change in the height of the point. Okay, so we should expect sine to be growing sort of rapidly from 0 degrees to, like, pi over 4 radians. And then from pi over 4 radians up to pi over 2 radians, the rate of change is kind of slowing down. So what does that look like on a graph? Well, it looks like we're going up at a good rate, and then we're kind of peaking and slowing down as we arrive at this peak here. And then we do the opposite. We go down, we cross through pi, and then we go through, oops, no, don't, oh God, no, not that, okay. We're good, everything's fine. And then we come down here through this point and then up through 2 pi. And our graph looks somewhat like this. Okay, and one key thing that I want you guys to notice, okay, is since sine of 2 pi is periodic, I know how to draw, not sine of 2 pi, sine of theta is 2 pi periodic. So I know how to draw the rest of this graph based on the following virtue. If I want to know what does the graph look like at, say, 5 pi over 2, well, I know that 5 pi over 2 minus 2 pi is equal to 5 pi over 2 minus 4 pi over 2 is equal to pi over 2. So since sine is 2 pi periodic, I know what the height of the function should be when the theta coordinate is 5 pi over 2. It should be the exact same height as the height of the function when theta is pi over 2. So all I'm going to do from here is the following. Let me see if I can do this in a really nice way. I'm going to erase this and I'm going to try to draw this in one smooth, fluid motion. Okay, if I want to know what to do from here, all I have to do is take all of the coordinates which I had before and basically, okay, well, I shouldn't have done that. I meant to duplicate. Bam. We just take this guy and copy and paste it over, okay? We just take the exact same thing, which was over here, and we copy and paste it over. And the function just continues to repeat itself like this over and over and over again. Okay? So if we pick some random point here, like this orange one, once we know all of the values of sine which lie in this orange box, then if we want to know how we find the height of the function at this orange point, all we have to do is go back to pi and find, well, what was the height of the function before? Okay, or if we're really far out, then we just copy that whole thing over again, right? Let's duplicate that again, and then we move it over. And it just carries on like this forever and ever. And if we want to know, well, what is the point, what is the height of this point here? Well, all we have to do is go back a multiple of 2 pi until we get into where we already had graphed, and then we copy that point all the way over there. So this is really why I talked about this periodicity stuff, is that the height of the function at a given point, which is very far away, all we have to do is trace back and back and back and back and back and back until we get to a point where we know where the function height is, and we just copy that function height over. Okay, so in this case, the distance between the two green caps is exactly 4 pi, and the distance between the two orange points is exactly 2 pi. And this is how we graph a trigonometric function. We basically just graph however much we need in order to express every single value that it takes in its periodic cycle. And then we just copy that, you know, in perpetuity in both directions. So I can copy this again and move this one over to the left. And that's what it's going to look like for all these negative angles, okay? All the negative angles, like here is negative pi, Here is negative 2 pi. Here is negative 3 pi over 2. And this is the point negative pi over 2, and so on and so forth. Okay, so I just copy this thing, and it just looks like this repeating cycle over and over and over again. Okay. By the way, if there are any musicians in the class, this is how we feed signals into speakers and amplifiers. Okay. In fact, if you record my voice right now and you essentially slowed it way down, my voice essentially sounds like at any given time like a sort of like a vibrato type of thing. And it's actually, it will look a lot like this graph. Okay. And depending on whether my voice is speaking in like a high pitch or in a lower pitch, then that will affect how this graph looks like in certain ways. You might have heard people talk about frequency and say, well, if you have a high frequency sound, it sounds very high pitched like a mosquito. And if you have a really low frequency sound, well, that sounds like the bass. Okay, so if you have like a subwoofer in your car, you might know that it has like a certain range of hertz. It might go down to like, I don't know, 10 hertz or something like that, or megahertz. No, yeah, 10 hertz or something like that. Anyways, so based on how these graphs look, we can produce all sorts of different sounds by feeding them into like a signal processing unit, like a speaker. Okay, we'll talk about that stuff more in a minute. Okay, so recall, sine of theta is what we call 2 pi periodic, which means that if we take theta and we add 2 pi to it, then the value of sine will be the exact same for that new angle. Okay, in fact, this is true for if we add 2 pi times any number n, where n is an integer. Okay, if n is an integer, then we add 2 pi times that integer to theta, and we get the same value. Okay, so this is how we graph sine of theta. Let me pause for questions. Any questions about how we made this picture here? No questions? Okay. Well, let's move on and try cosine of theta. Okay, for this one, I'm going to use sort of the same values. If you wanted to make this graph really nice and complete, you could put pi over 4 in here and like 3 pi over 4 and so on. But I find the value of sine at like a pi over 4 will be something like square root 2 over 2, which I find sort of hard to understand where in between 0 and 1 this number is. So I don't usually like to graph those ones. But you could if you wanted to, and it would go something like this. You basically copy over each of these heights at pi over 6 and pi over 4 and pi over 3 and whatever, if you want. I basically am basing my knowledge on the fact that I know that the graph should look sort of curvy like this, And I'm just going to plot, okay, where are the points where it goes through 0 and where are the points where it reaches its maximum values. And that's kind of enough for me to draw the graph because I kind of know already what the graph should look like. So that was that argument that I gave you guys sort of about how when the angle is close to 0, well, we're going up kind of fast in terms of the y value. If for a small change in the angle, the y value goes up by a lot. When we're close to pi over 2, a small change in the angle is going to make the y value only go up by a tiny little bit, which is why when we're very close to 0 here, it looks like we're going up at a pretty fast rate. And when we're very close to pi over 2, we're going up at a more gradual rate. Okay, so I'm just going to make these graphs, they should just look, they should look kind of nice and curvy like this. And I'm going to point out where their maximums and minimums are. And I'm going to do that because I know that the maximums and minimums of these functions occur at these values where we have the points like 1, 0, you know? Okay, so let's draw a let's draw a unit circle here. Okay, so cosine theta. To do this one, I'm just going to take these points in here, these not points, these angles theta. And now I don't want anybody to get too confused by this because we're saying that the y-coordinate of the graph of this equation is going to be given by the x-coordinate of the point on the unit circle, which corresponds to the input theta. Okay, so it's a little bit confusing because we're talking about y here when we're talking about the function, but the cosine is actually referring to the x-coordinate of the unit circle. So here's how we do that. Well, if we want to know what should the y-coordinate of y equals cosine theta be when theta is equal to pi over 2, well, I draw the angle pi over 2 on the unit circle. It looks like a right angle. And I want to look at this point here, which is the point 0, 1. And if I want to know how tall should the graph of cosine theta be when theta is equal to pi over 2, the height of it should be equal actually to the x-coordinate of this point on the unit circle, which corresponds to pi over 2. So when theta is pi over 2, the graph of y equals cosine of theta is going to be equal to the height of it is going to be equal to the x-coordinate, which corresponds to that point on the unit circle. So I'm going to put a 0 here at pi over 2. In fact, I also know from the fact that I already computed the zeros of cosine theta, I know that cosine should also be 0 at 3 pi over 2, and at 5 pi over 2, and 7 pi over 2, and so on and so forth. And now I just need to figure out, well, how do we draw the rest of it? Well, if we consider the theta value to be 0 here, well, let's check what is cosine of 0. Well, if my angle is facing directly to the right, okay, so this is theta equals 0 radians, then the point on the unit circle here is the point 1, 0. And the x-coordinate of that point is 1. So that's the cosine of theta is 1 when theta is equal to 0. So I make the height of the function equal to the x-coordinate on the unit circle, which corresponds to the angle 0, and that x-coordinate is 1. So the height of my function when the theta coordinate is 0, the height should be 1. And then so on and so forth. It should be -1 when theta is pi. It should be 0 when theta is 3 pi over 2. And then the last one I have to do is just 2 pi again, which faces, again, 2 pi is just all the way around and then facing again in this kind of positive x direction. So we get the point 1, 0 yet again. And we're going to go back up to 1 at this point. So if I want to draw this in, well, it should look basically like this. Okay, and if I want to know how to continue the graph, since I've already done everything, which is from 0 to 2 pi, I know the rest of the graph is just going to be copies of this thing. So I'm just going to copy and paste, and here comes the next part of the graph. And then I'm going to paste again, and it's just going to keep going like this, on and on forever. And you notice this looks quite a lot like the last one we did. Nice and curvy like this. Okay, except there's a major difference between this graph and the other graph we drew. Let me see if I can show you by doing the following. I'm going to try to overlay these really quickly. Let me see if I can do this. This is going to get really busy. You can see that these... Okay, you can see that these two graphs do have a major difference. Although they're the exact same shape, one of them is moved over. Okay, one of them's moved over. So this is a major difference between these two graphs, is that the pink graph of sine theta is taking completely different values from the cosine graph. Okay, so they look the same in terms of their shape, but in terms of where that shape lies in the coordinate plane, they're very different. Okay, so cosine starts up here at 1, and sine, okay, sine starts at 0 and goes up. Okay, whereas cosine starts at 1 and goes immediately down, sine starts at 0 and goes immediately up. So pretty big difference there between those two. Okay, I'm going to delete this. Okay, so this is how we do cosine. And let me make a quick remark about the following. Remember, way back when, not that long ago, oh wait, when did we talk about that even? Not that long ago, we talked about when are these sine and cosine functions going to be even or odd. And we established, okay, that sine of theta is an odd function and that cosine of theta is an even function. So remember, an odd function is symmetric about the y-axis, and an even function is symmetric about, odd function is symmetric about the origin, and an even function is symmetric about the y-axis. So let's see if we can actually see that in the graph of y equals sine theta and y equals cosine theta. Well, if we look at the graph of cosine theta first, we can see that if we take some point here, if we take some point like at 2 pi, okay, look at 2 pi, well, the graph of the function at the point negative 2 pi is exactly the same. It looks like this is in the mirror world, okay? We've been reflected over, okay? So essentially, it's like on this highlighted axis here, the y-axis, it's like there's a mirror, and it looks the same on both sides. It's symmetric, okay? So this is why cosine is an even function. Well, it's not why cosine is an even function, but it's a property of the fact that it is, or a consequence of the fact that it is going to be symmetric about the y-axis. And likewise, for sine, okay, it's symmetric about the origin. If I take a look at this point here, Well, the way I get the point, if this is x and then this is negative x, well, I just take a line which goes straight through the origin. And that's how I get the height of the function for negative x. Okay, or if I consider this point, which is down here, I take a line which goes straight through the origin, and that's how I get the point for this one. If this is like negative x1, and then this is x1, okay? It's symmetric about the origin. So we can see sine of x as an odd function. Okay, so this is kind of a lot of information here, but it's all like a spider web. It's like extremely well connected to one another. Okay, we have these properties of these functions being even and odd. We know where their zeros are. We know they're 2 pi periodic. They're nice and smooth. They come from this unit circle. So there's a lot to connect here. But what that means is essentially, if you have like, if you have some spider web or something which is like extremely well connected, okay, and you want to get from point A to point B, it kind of gives you a lot of options, okay? We can take any number of routes that we want to get to this point. We can take this route, or we can take, I don't know, we can take some other crazy route. We can go like, around this way and then in and then there. We can do whatever we want in terms of that. So it's really kind of nice that all this stuff is so well connected, okay? That most of the time we have a lot of freedom to choose the way that we approach a given problem. Okay, so once we have the basics down about these graphs, we can ask all sorts of questions about like, these trigonometric functions and how they are different from one another and how we translate them and how we can relate the two and how we can talk about all the other trig functions. It's all extremely well connected, and you can probably make a lot of different arguments to make the same exact point with these things. I feel like that dude from It's Always Sunny when he's got like the board with everything connected. Let me see if I can find that one. His name's Charlie, I think. Yes, this is the one. This is what I feel like. It's all connected, okay? Everything is like this crime web here. It's all super connected. Okay. Questions so far? Not a question, but I'm appreciating that GIF a lot more. Yeah. Wait, which GIF are we talking about now? We talking about maybe talking about this one here? Was that what we were talking about, Heidi? Yeah, okay. Sorry, I totally missed your comment there. Yeah. Yeah, so this is, essentially what we're doing. Okay. All right. So let's carry on then. Unless, let me pause and make sure there's no questions first. Yeah, Always Sunny is great. I agree. Are there any questions about how we made these graphs of these trigonometric functions, or about some of the comments that I made about how they're 2 pi periodic, or about how they're even or odd, or how they relate to the unit circle? Okay. There's no questions? Then let me give a little bit more information here. Okay, so let's talk about some words. Okay, I know this is a math class, but we're going to have words today. All right, and the words that we care about mainly are the following. We like the word period. It describes something about our periodic graph. And we like the word amplitude. It's also going to describe something about our periodic graph. Okay. By the way, sometimes people call these waves. Okay, they call them sine waves or cosine waves. And well, I think the reason is pretty obvious. These look like the waves of the ocean. Okay, where maybe they're moving in this direction. Okay, and over here is the beach, and over here is like the deep ocean. Anyways, so the anatomy of a wave is as follows. We have the period of the wave, okay, which describes the length between two crests, okay? The length between two crests of the wave, okay? That'll be the period. And the amplitude will be the height of each wave relative to the, flat surface of the water. Okay. So it's not exactly describing the, distance between the crest and the swell or whatever. I don't know how you call the bottom part of the wave. It's not talking about the difference between the peak and the valley. It's talking about the difference between the peak and regular sea level. Okay, so that's what amplitude is. Okay, so say we have a function which is y is equal to sine of bx. Okay, this is what we have in here, right? Then the amplitude is going to be the wave height. Okay, in our case, depending on what this number a is, which we multiply by sine, it's going to change how high our wave is. Okay, so if we take the sine function, which we know goes from -1 to 1, and we multiply by a, well, it's going to go from -a to a. Okay, so the bottom is -a. Down here is -a. And up there is a. Okay, and depending on if a is like a billion or 1/10, this can change the height of our wave. Okay, so we take the absolute value of that thing, okay, which, remember, it's possible for a to be a negative number, in which case our graph would look more like this, right? But still, we take the absolute value of it, and it's going to describe the height of a given wave. Okay, so we take absolute value of a, and this gives us the amplitude of a sine b of x, or a sine of b times x. Okay, so that's the wave height, which is vertical. And then we have the period, which describes the distance from crest to crest. Okay, and we know that sine of bx is 2 pi periodic. So we know that sine of theta is equal to sine of theta plus 2 pi. Okay, so if we take sine of bx, well then sine of b theta, right, is equal to sine of b theta plus 2 pi. And if we bring the 2 pi inside the b theta, we get sine of b theta is equal to sine of b times theta plus 2 pi over b. So we get that sine of b times x will be is 2 pi over b periodic. Okay, so this b here is going to scale things somewhat. Okay, so instead of going from 0 to 2 pi being one full kind of wave, our wave goes from 0 to 2 pi divided by b. Okay, in other words, this b here is giving us like a horizontal compression or a horizontal, man, I wonder if I can do that actually. Let's see here. This is just a test. See if I can, oh no, I can only scale like this. I wonder if maybe if I go like this, maybe I can scale both ways. No. Style? No. Man, I wish I could like go left and right, you know, or up and down, but not diagonally. Okay, whatever. Anyways, this B here is going to give us either this B is going to give us either a horizontal compression or a horizontal stretch. So you can imagine taking this sine wave and basically like a slinky, either pulling it out or pulling it in, and the crests of the wave will get either closer and closer together or further and further apart. Okay, so if we compressed this one, it would look more like this, right? If we compressed it. So if we pushed it in like a slinky or a spring, it would look more like that. And if we pulled it out, well, then it would look more like this, okay, and be like much further between these things. Okay, and that's going to affect the period, which is the distance between the crest to the crest. Okay, and the period basically expresses the amount of length which it takes for us to do one whole wave. Okay, which is, you can think about it as going from, you know, 0 to 2 pi over b like this. But the reason we call it the length from crest to crest is because sometimes this can be misleading for students who are first trying this out, because they think, well, the period then is just from whenever I cross the x-axis to the next time I cross the x-axis, but that's only half of the entire wave. But if we consider it as going from crest to crest, well, there's no way to get confused and do only half of the wave. That's always going to be a whole wave. Okay. All right, so that is about period and amplitude. Man, I have just been, there's just so much to say about this stuff. I'm starting to get a little bit behind. Can't believe it's 9:43 already. All right, well, these are how we define these words. Okay, we call them the amplitude and the period, okay, which are going to be respectively the height of the wave and the distance from crest to crest. And each of them are going to depend on these values of a and b, which we might have y equals a sine b of x, or we might have something like y equals a cosine of b times x, right? And these are our basic like transformations, which we're going to have for our trigonometric functions, as well as all of our other functions, right? A, if we multiply by something out front, it's going to produce a vertical shift or a vertical shrink. And if we have a b here, well, it's going to produce a horizontal shift, a horizontal compression or a horizontal stretch. Okay, and likewise, if we add something out back, plus c, well, then that's going to move everything up or down. And if we have a subtraction inside, well, it's going to move things left and right, so on and so forth. Okay. All right, I really don't think I have time to actually start talking about a phase shift right now. So we'll talk about phase shifts next time. That's going to be our horizontal shifts. And then we'll talk about how to actually graph these things when we have a full setup of shifts and shrinks and compressions and in all sorts of different which ways, and maybe some reflections too. But I think I'm going to call it for today. I think you guys have had enough trig. So that's it for today. I hope that you found this lecture as thrilling as I did. I really like talking about this stuff because it's just so interconnected. But anyways, everybody have a great weekend. I hope you rest up, and we'll continue our discussion on Monday. Yep, my pleasure. Yep, you too. Shruti, did you have any questions about the lecture or the class?